Hello everybody and welcome to this session on Exploratory Data Analysis or EDA. I am Dr. Andrei Holtz and I would like to share with you insights from years of research and practice in machine learning and data science. This is the first lecture in machine learning lectures, and EDA is an essential step that not only helps you understand your data, but also guides every subsequent decision in your data projects. Whether you're cleaning data, engineering features, or choosing models, a robust EDA process is the key to success. And let us move on. What about the agenda? So, today's lecture is structured into several major parts. We will start with an introduction to EDA. Next, we will cover basic analytics and how to deal with different types of data. Then I'll show you how automation tools can streamline your workflow. We will also explore visualization tools and techniques, and finally, we will discuss common challenges in EDA and how to overcome them. This journey is designed not only to build your technical skills, but also to show you why EDA is critical and and help you avoid pitfalls later in your machine learning projects. Before we get into the specifics of EDA, it is important to understand its role within the broader data analytics pipeline, like CRISP-DM or cross-industry standard process for data mining. It provides a structured approach from understanding the business problem through data preparation and modeling to evaluation and deployment. And this is a cyclic process, and that's basically an industry standard in some cases, in some companies, in some industries. So I highly recommend taking a look at it. You can have some information on the link below here. And this is one of the best methodologies to deal with the data. Of course, there are other methodologies, but if you're starting from scratch, I believe it's worth taking a look. And what about the EDA? So EDA is a part of the data understanding phase. There are a lot of phases, and you can take a look at them here, but by following those phases, you ensure that every step you take is both systematic and aligned with your project goals. So again, as I said, review the links, and this slide will also help you to understand the framework, but let us focus on the data understanding and EDA. So what is EDA? Let's find out. EDA, or Exploratory Data Analysis, is the process of diving into a dataset to understand its structure, identify patterns, and detect anomalies. And this is the first step in any data analytics project, performed before any formal modeling or hypothesis testing. The goal is simple: to turn raw data into insights by using summary statistics and visualizations. This fundamental understanding helps you guide every decision you make later. So again, before doing any modeling, before everything, you need to take a look at the data and understand whether this data makes sense, what this data represents, and what are the statistics, what are some maybe insights you can get from this data. And this will be the foundation of your next hypothesis, of your next analysis, and of the models that come after this. So EDA serves as the bridge between raw unstructured data and actionable conclusions. By performing descriptive analysis, adjusting variable types, treating missing data, and identifying outliers, you create a clear picture of your dataset. This process not only uncovers hidden relationships, but also guides you in refining your approach for feature engineering and model selection. In essence, EDA is what transforms disorganized data into a compelling narrative that informs your entire analytic process. And what about the objectives? Yeah. Um, let's break down the key objectives of EDA. First one, understanding the data structure. It helps you see how variables interact. Then it's spotting patterns and relationships. It is essential for uncovering trends or clusters. Identifying outliers is critical as these can skew your analytics if left unchecked. Assessing data distribution, whether it's normal, skewed, or multimodal, informs your choice of statistical methods. Moreover, EDA guides feature engineering by highlighting which variables may need transformation or scaling, and handling missing data early prevents future errors, and by reducing the risk of incorrect assumptions, you can select the right model for your predictive task. And each of these elements is vital for building a robust analytical pipeline. Let us talk a little bit about data types and basic analytics. Data comes in different forms, and the first step in EDA is to recognize these types. Data can be broadly categorized into several types: numerical, categorical, ordinal, and time series. So numerical data includes continuous and discrete variables, while categorical data uses labels like gender or color. And the example of numerical continuous value is like price or like liters of gasoline. Ordinal data has an order, such as ratings, like movie ratings from 1 to 5. Time series data is collected over time and requires special handling due to trends and seasonality. Imagine something like stock price. And recognizing these types ensures that you apply the right statistical tools and visualizations and models for accurate analysis and for accurate modeling. For example, for numerical data, we use summary statistics such as mean, median, and standard deviation. For categorical data, counts, proportions are more relevant. The initial analysis lays the groundwork for everything else that follows. So, what about the key statistics? Key statistical measures in EDA for numerical data. The mean gives you the average value. The median provides the middle value when the data is sorted, and the mode represents the most frequent occurring value. And they are called measures of central tendency. Measures of data spread. To understand variability, we use standard deviation and variance, which tell us how much the data deviates from the mean. And as for the indicators of distribution shape, we use skewness that informs us about the asymmetry of the distribution, and kurtosis that measures how heavy the tails are, and they are essential for spotting potential outliers. And together, these metrics provide a comprehensive summary of the feature's behavior. So, in an ideal scenario, A dataset exhibits zero skewness, meaning that the mean, median, and mode are all equal. This condition is characteristic of a perfectly symmetrical distribution, often approximated by the normal distribution. When these measures diverge, it signals that the data might be skewed, which could have implications for statistical tests and model performance. Recognizing this can give you the idea to apply transformations or choose alternative methods to ensure accurate analysis. Not all datasets, not all features are perfectly symmetrical. In many real-world scenarios, you encounter skewed data, and positive skewness occurs when the tail on the right side is longer, with the mode being the lowest, followed by the mean, and then followed by the median, and then the mean. On the other hand, negative skewness indicates a longer left tail, with the mean being the smallest value. Understanding these differences is crucial because the skewness of your data can affect the performance of statistical tests and predictive models, and often transformations are necessary to achieve a more normal distribution. Kurtosis means the tailedness of a distribution. Its names come from the Greek word of curved, and there are three types of kurtosis. Mesokurtic distributions, which are close to normal, leptokurtic distributions, which exhibit a sharp peak and heavy tails indicating a higher likelihood of extreme outliers, and platykurtic distributions, which have a flattened peak and light tails. And knowing the kurtosis of your data can alert you to potential risks of extreme values, which is especially important in fields like finance or risk management. Let us take a look at the illustration of kurtosis. And as I mentioned, the leptokurtic with heavy tails, mesokurtic, and platykurtic with light tails. Okay, so when it comes to calculating the statistics, modern data analysis relies heavily on tools like Pandas, NumPy, and SciPy. Each of these libs offer functions to compute means, median, variance, and more, often with options for bias correction. And understanding how these tools work and the assumptions they make is crucial for ensuring that you computed statistics accurately and that the statistics you calculated reflect your data. Of course, if you have some requirements that maybe you cannot use those libs, you can write your own custom functions and calculate the statistics. But please keep in mind that you need to understand all the assumptions and you need to understand what exactly you are calculating. Central tendency metrics like mean, median, and mode are fundamental in summarizing your data. Again, as I said, you can either use something from Pandas or you can calculate them on your own. They will return the same result. Again, keep in mind that knowing which measures to use and why is essential for correctly interpreting your data center and making decisions based on it. Variance and standard deviation are also can be calculated either with one function from Pandas or by creating your own function and calculating it. A low standard deviation indicates that the data points tend to cluster around the mean, whereas a high standard deviation signals more spread out values. This insight is critical as it informs how much trust you can place in your average values and how you might need to adjust your models to account for variability. Skewness and kurtosis go beyond basic measures and they help us understand the overall shape of the data distribution, as I said. When it comes to write statistical tests or deciding whether transformation is needed, uh, please calculate the statistics. Keep in mind that if you calculate the kurtosis, there are several options to calculate it, and sometimes the version is biased. So it is important to note that. And the methods to calculate statistical measures can introduce bias. For instance, many functions include an option for bias correction, and ignoring these can lead to underestimated variances or incorrect inferences about the data distribution. Always check whether your calculation method accounts for bias. This attention to detail ensures reliability and accuracy of your analysis. As in this example, you can review it and you can even try it. And Fisher's definition of kurtosis adjusts the raw value by subtracting 3, which sets the kurtosis of a normal distribution to 0. This adjustment simplifies comparison between your dataset and the normal distribution. It helps highlight whether your data has heavy or light tails relative to what's expected in a typical bell curve. And this is useful in ensuring that any deviation from normality is a subject to investigation. When working with categorical data, the approach differs slightly. You look at frequency counts to see how often each category appears. You calculate proportions to understand their relative frequency and identify the mode as the most common category. Additionally, tracking the unique count gives you insights into diversity, and understanding missing values is crucial to avoid skewed conclusions. These metrics provide a clear, concise picture of how your categories are distributed. And now, let us have some coding practice. Welcome to this demo, and we will start with reviewing the dataset. First of all, we will need to connect to Google Drive to access the dataset, then import the libs that we'll be using. I'll be using Pandas, NumPy, SciPy, and some other. And um, we'll load the dataset and get the descriptions of this dataset since they're available as a separate, let's say, document. And this dataset contains information about households sold in Ames, Iowa, including various numerical and categorical features that describe properties and their characteristics. We begin by connecting to Google Drive and we ensure that we can access it, and we then load the dataset into Pandas data frame. We'll load it as a Pandas data frame, treating NA or treating missing values as NA. This is important because handling missing values data effectively can significantly impact analysis accuracy. And let us just inspect the first 10 rows. So we have some ID and some data. Basically, we have some data. Sale price here, sale condition, sale type, and whatever. We can use this method to show elements of the first row, this one, as a dictionary. to review it in a way. But again, let's move to the dataset, and we use df.info to get the basic info about the dataset. Here we have like the number of non-nulls and the data type, the estimated data type, and the column name. So we have 2,930 entries, and like the memory usage of the whole data set. And we can have the statistics here by using data frame describe. It provides summary statistics, allowing us to spot some basic information about the data set. However, if you take a look, that's a numerical data. We can again show the statistics for one field, but what if we would like to get the information about the, let's say, object data, or I mean, if the data is categorical and we would like to see some categorical statistics, yeah, like count, like number of uniques, frequencies, and so on. We can do this, and here we can calculate the number of unique values for some, let's say, fields here, and we can use descriptive statistics of numerical value, also like this, and we can calculate descriptive statistics of numerical values for all of them, or calculate it for other types of data by excluding some types of data, like here. So here we have estimations of data types. It's not always the best match here. What I mean by this is, if we calculate the total memory usage here, well, that's 7 megabytes. But let us detect the column type and specifically set it to either Boolean or categorical, because Pandas data frame supports categorical. We'll use the category threshold. It's the proportion of threshold for categorizing column based on uniqueness. Like if the column has a lot of unique values, well, let us treat it as a categorical. And yeah, we can define the numeric type here also. Either like if we have only 2 unique values, let's treat it as Boolean or binary. And detect object type, we'll again use categories and just objects. So let's try to apply this function, yeah. And we have the reduction of total memory usage here. So like after types adjustments, it dropped down like 7, almost 8 times. Yeah. Pretty impressive, I would say. So what about the statistical measurements? So let's take a look. We can calculate by hand the mean, the median, and the mode, or we can calculate the same values with NumPy by providing the data here. Yeah, we can calculate mode. We can calculate other statistics, and they are similar, or I would even say same, because, well, we calculated it in a pretty good way. We can also use the pandas functions that are provided. Not a big deal, we can use it. And as for the and this is like the measures of central tendency. What if we want to calculate the data spread, standard deviation and variance? We can do so. We can use the formula, the existing formula, and calculate them by ourselves, or by using, let's say, NumPy or Pandas data frame calculation. And by default, NumPy's standard deviation and variance functions calculate the proportion standard deviation and variance, while Pandas corresponding methods calculate the sample standard deviation and variance. Those are different. The difference is in the denominator used in calculations, and it leads to slightly different results, as you can see here. Here, here, and here. And to make Pandas calculations match those of NumPy's default behavior, we can set the parameter to 0 when calculating the methods, and we'll get the same value. What about indicators of distribution shape, skewness and kurtosis? We can do so. We can either calculate them by hand, like this, using formulas, or calculate using SciPy methods or Pandas methods. Or like some, let's say, other methods with bias switched off. We can notice that the data will vary. And that's okay, as I mentioned in the lecture. So you need to keep in mind that you need to have this bias adjustment. And what about the categorical data? You can calculate frequency counts by using value count in pandas, like this, or you can have some kind of function like this and calculate the value counts, mode, number of uniques, missing values, and create yourself a nice looking report. That's it for this part. Welcome back. Now let us focus on univariate analysis. It involves analyzing one variable at a time. Univariate analysis aims to understand the distribution, central tendency, and spread of the variable. And the key objectives here are identify patterns, like detect trends, anomalies, and outliers in the data, measure distribution, like understand whether the data is normal, skewed, or bimodal, aid in data cleaning. It helps spot missing values or inconsistencies that need corrections. To effectively explore a single variable, we have a range of visualization techniques to use. Histograms allow us to see frequency distributions clearly. Kernel density estimation smooths out the noise to give us a continuous view of data density. Empirical cumulative distribution function, or ECDF, plots of this function helps us understand cumulative distribution and percentiles. Box plots summarize key statistics and highlights outliers. And violent plots provide a dual view of statistical summary and data density. And each method serves a unique purpose, and when used together, they offer a complete picture of your data. Histogram is one of the most straightforward visualizations available. It groups data points into bins and displays the frequency of observation in each bin. This simple yet powerful tool allows you to quickly assess whether your data is normally distributed, skewed, or even bimodal. For instance, if you see a long tail on one side of the histogram, it indicates skewness, a clue that you might need to apply a transformation before processing with further analysis. The histograms are simple to calculate, simple to plot, and use it wherever it's possible. Kernel density estimation, or KDE, is a non-parametric way to estimate the probability density function of your data. Unlike histograms, kernel density estimation doesn't rely on fixed bins. Instead, it produces a smooth curve that gives a better visualization of the data's underlying structure. This is especially useful when you are unsure about the form of the distribution and need a continuous approximation to guide further analysis. And ECDF, or Empirical Cumulative Distribution Function, plots the cumulative probability of each data point. This visualization shows you how data accumulates over its range, which is incredibly useful for understanding percentiles and the overall spread of the data. With an ECDF, you can easily identify what percentage of data points fall below a certain value, and this is important insights for many statistical analysis. Again, it's also easy to calculate and use to plot. A box plot is a powerful yet simple tool that displays 5-number summary of the feature or of your data. The minimum, first quartile, median, third quartile, and maximum. What makes boxplot particularly useful is their ability to highlight outliers, those data points that deviate significantly from the rest. The outliers for the boxplot are calculated like Q1, or like the 25th percentile, minus 1.5 multiplied by IQR, and this is the minimum, and everything lower than minimum is outlier. The same logic applies to maximum, and maximum is like 75th percentile, or Q3, and you have Q3 plus 1.5 multiplied by IQR, and this is your maximum, and everything above this maximum is an outlier. And interquartile range, or IQR, that's basically the difference between Q3 and Q1, or like 75th percentile and 25th percentile. So this quick snapshot is valuable when you're looking to assess the central tendency and spread of your variable at a glance. But box plots can be improved, and violin plots take the concept of a box plot and enhance it by incorporating a EDA curve. This combination not only shows the 5-number summary, but also provides a visual representation of the data density. And for data sets with complex distributions, a violin plot can reveal nuances that a simple box plot might miss, offering a more complete picture of the data's shape. And this is the example. So again, the data is specifically generated in order to have the same box plots for the raw data and for like synthetically raw data, but like box plots look similar, and they are similar. However, for the same data, the violin plot will show you like there is a difference. Let's have some coding And welcome to Univariate Analysis demo. It focuses on analyzing individual variables independently to understand their distributions and characteristics. And we start by exploring sale price, one of the most critical variables in this dataset, since it represents the selling price of a house. And to understand how it is distributed, we need to compute quantiles which divide the data into different percentiles. This helps us determine thresholds such as median, which is the middle value, and quartiles, which help identify lower and upper limits for pricing trends. And we can do so by using Pandas function. Next, we're moving on and to use histogram to visualize how frequently different price ranges. So we create this histogram using either Matplotlib or Seaborn. And histograms are essential because they provide a visual representation of the data distribution. We can do so easily. So the number of bins that we're dividing, the colors and titles and so on, the same here. As for the kernel density estimation, so to refine our understanding, we generate this plot, and it smooths out the distribution, giving us a continuous curve that represents density. We can do so by either calculating it like this and using Matplotlib, or by using Seaborn and printing it out. Both options are okay. We can make it nice looking like this with different colors and so on. As for the empirical cumulative distribution function, or ECDF, again, we can compute it, we can plot it. It shows the cumulative proportion of data points up to a given value. This is super useful. We can do so by using a Pandas approach, or say any other approach, but here is like the illustration how to do it in Pandas. Firstly, we calculate it by sorting and applying cumulative sum, and then just by plotting it. What about the box plots? They help us identify outliers and help us get the information about the data distribution. We can calculate them and plot them by using model boxplot in Matplotlib, or the function boxplot from model Matplotlib. We can also use the Seaborn implementation like this, or we can calculate like the IQR and all the numbers by ourselves. That's also an option. Moving on to the violin plot, it combines the representation of the box plot with kernel density estimation to show the distribution. We add markers for like mean, median, and mode, and we can use Seaborn violin plot to plot it. Just to illustrate the whole thing and make the illustration more interesting, so we can plot the mode, the median, and the mean by combining the Seaborn and the Matplotlib like this needed. And that's it for this demo. Welcome back. And we continue with bivariate analysis, meaning like what if we have two variables for our analysis. Now we explore how two variables interact with each other. And this is a crucial step in understanding dependencies and correlations, which are the backbone of predictive modeling. We'll also try to find trends between two variables and like how one impacts another one. And without this analysis, there will be no regression, classification, and any other predictive modeling. To analyze relationships between two variables, we can use a range of visualization techniques. For quantitative data, scatter plots and correlation matrices are very effective. For categorical data, bar charts and cross-tabulations are often the best choice. And when you have mixed data types, you may need to combine techniques to get the full picture. And each visualization method gives you a different angle on the data, enabling you to detect trends and dependencies that are crucial for building robust predictive models. A scatter plot is a simple yet powerful visualization that displays the relationship between two numerical variables. Each point represents an observation, and by examining the pattern of points, you can understand whether there is a positive correlation, where points slope upward, a negative correlation, where points slope downward, or no correlation at all, when points appear scattered randomly. Scatter plots also help identify clusters of data and outliers that might otherwise distort your analysis. A correlation matrix provides a bird's eye view of the correlation and relationships between multiple variables at once. So this table shows the correlation coefficients, and the coefficient ranges from -1 to 1, indicating the strength and direction of the relationship between variables. And it is useful when working with many variables to detect patterns in one view. So how to interpret? 1 indicates perfect positive correlation. -1 is perfect negative correlation, and 0, it's no correlation. However, keep in mind that correlation might not show you like the real dependency between variables, because some correlation coefficients are designed to only detect linear dependency, so dependency might not be linear. However, like the correlation heat map is incredibly helpful in quickly pinpointing which variables have significant relationships and deserve future exploration. And yeah, correlation does not imply causation, so keep in mind you need to double check everything. Cross-tabulation or contingency tables are great tools when you want to analyze the relationship between two categorical variables. These tables display the frequency counts for each combination of the categories, mm, enabling you to see patterns of mm, association or dependency. For example, you might use cross-tabulation or a contingency table to see how passenger class relates to survival rate on the Titanic. It's an excellent way to begin understanding the interplay between categorical variables before moving on to more complex analysis. So high counts in specific cells indicate a stronger association between categories. And here we have the distribution of overall quality across neighborhoods. We have neighborhood and like the count, like the overall quality, and we can see some patterns here also. Joint plot. A joint plot evaluates the concept of a scatter plot by adding marginal histograms or EDA plots along the axis. This combined view not only shows you the relationship between two variables, but also gives you an understanding of their individual distributions. This comprehensive visualization is perfect for understanding both the overall trends and the finer details of each variable's behavior. Again, you can see here the correlation, you can see the data shape here, and it contains more information than you'll just use scatterplot. There is another version of scatterplot is hexbin, and when dealing with very large datasets, a traditional scatterplot can become too cluttered, too noisy, making it hard to show any pattern. Hexbin plots solve this problem by grouping data points into hexagonal bins. The color intensity of each bin represents the density of data points in that area, revealing patterns that might be obscured by overplotting. This technique is particularly effective when you need to visualize density in a clear and organized way. What about bar plots? Bar plots are among the simplest yet most effective ways to compare a numerical variable across different categories. Whether you're comparing average incomes across regions or the number of occurrences of different classes in a dataset, bar plots allow you to quickly and clearly see differences between groups. Their simplicity makes them ideal for presenting data to a wide range of audience. For example, it's ideal for categorical data such as gender versus salary or education versus income. A pair plot, it's a powerful visualization that creates a matrix of scatter plots showing every possible pairwise relationship among your numerical variables. And this comprehensive view allows you to detect correlations, clusters, and anomalies across multiple dimensions simultaneously. It's an excellent tool for the early stages of data analysis, where you need to quickly look at the data and decide which variables interact with one another. It's a great choice for exploratory analysis. However, it might take some time to plot. And in today's demo, I'll show you how to create scatter plots, correlation matrices, and other visualizations. And this is bivariate analysis demo. In bivariate analysis, we explore the relationship between two variables. Let us review the sale price and ground living area. So a scatter plot here helps us see how house size influences price. We can do so by using Seaborn, by having this scatter plot, but it's not as informative as we would like it to be, although we can see like the slope here, but let's try to build it with a regression line and like correlation coefficient. We can do so just by providing the relevant parameters here, and yeah, we can have the regression line. And what if we would like to have like the coefficient, the Pearson correlation coefficient, and the exact equation of the line? We can do so. We'll need to apply stat models to perform a linear regression just to calculate this line. We can calculate the Pearson coefficient. Pearson correlation coefficient can be calculated here. And yeah, we can add everything to this plot, what we can say is there is definitely a correlation between the sale price and the ground living area, and it's a positive correlation. So bigger houses have higher prices, and we can like make this conclusion just by looking at this graph. And let us move to the correlation matrices. We can calculate them using the uh, standard Pandas approach. So there are different correlation coefficients that can be used here, like it's Pearson, a Kendall, and Spearman. And it returns the correlation matrix. This matrix helps us analyze multiple numerical variables at once. And we can plot this heat map. What we can say by looking here is that the closer coefficient to 1, the more the data is correlated, and we can just make this decision by looking at this correlation heat map without looking at some numbers, some coefficients. And using correlation, let's say, characteristics, we know that this matrix can be diagonal, since like the diagonal value here is always 1, and the data is symmetric, so we can just utilize a part of the whole heat map, the lower triangle, for example. What about the cross tabulation? Well, for example, we examine how overall house quality varies across different neighborhoods using a heat map. This helps us understand regional differences in home quality. We can do so. We'll need to calculate the crosstab of the overall quality in the neighborhood, and then just use the heat map. And here you have it. As for the joint plot, we can use Seaborn to just plot it. However, we can make it like even fancier by combining the scatter plot, the nice scatter plot, with the regression line coefficients and Pearson correlation coefficient and the R squared of this line, and by providing really insightful information like mean, median, and standard deviation of the features. We can do so by calculating everything, by providing this information and adding statistics for access by using Matplotlib and Seaborn. That's how we do it. Again, the hex plot being it's not a big deal to calculate it using like Matplotlib. Can calculate it like this. You can use the color bar, and you can even make it more, let's say, fancier by using this joint plot and having not like the previous version, but combining with the hex bin. And as for the bar plots, well, that's a standard thing. Actually, we can use the Seaborn and just provide the values here, the features here, and here you are. You can calculate them. However, we can make it like even fancier, and that might be more, let's say, informative and more nice looking, because here we can have like the standard deviation value, we can have the exact values here, and so on. This is the code, you can review it. There are some pandas calculations, Seaborn calculations, like we're adding exact values, but again, we can do so. And what is interesting here is that it's the number of garage cars. We can see that the average sale price by the number of garage cars is limited to 3, and then it falls, but for some reason we have no standard deviation for the 5 number of garage cars. Just a spoiler for you, it's because we only have one value of this in the dataset, so from one value we cannot calculate the standard deviation. And we can also calculate the box plots for this distribution. And this clearly shows that, well, we have only median. We do not have any data except one measurement, unlike the others. Because this might trick you, because you do not clearly see like how much data do you have. And here you can see it. Yes, and as I said, there's only one entity with these parameters. Again, we can group the data by using pandas group by, apply aggregation functions, we can sort them. So here what you can calculate and do just by using pandas. You can also calculate uh, the thing using pivot table, just to simplify things. And again, pair plot. You can have the pair plots here by using Seaborn pair plot. You just need wait a little bit and it will be calculated. And that's it for this demo. Welcome back. Okay, but what if we have more than two variables? Well, that's where multivariate analysis comes into play. As we shift our focus to this type of analysis, multivariate analysis, we analyze three or more variables simultaneously. And this phase is crucial because real-world data rarely exists in isolation. Instead, multiple factors interact in complex ways. Multivariate analysis lets us expand our view from isolated pairs to a broader picture. And by considering several features at once, you can uncover some complex patterns and interactions that are invisible in simpler analysis. The difference between seeing a flat, two-dimensional picture of your data and understanding its full multidimensional complexity. And this is the key for building accurate models and understanding how different variables influence each other. Let's have some examples. So, 3D scatter plot. It extends the conventional two-dimensional scatter plot by adding a third axis, allowing you to visualize the relationships among three variables simultaneously. This added dimension can reveal clusters and trends that aren't visible in 2D. Of course, 3D plots sometimes can be more challenging to interpret, but they are useful when you need to show like the 3D picture or some more complex interactions. Moreover, you can add the fourth dimension like coloring, and there will be four variables shown here. And even more, if you add different size and shape, you can have like 5 or 6 variables shown in one picture. But sometimes it's a challenge to understand like what is going on. So you need to balance between the complexity and the simplicity of your visualization. Building on our earlier discussion of violin plots, we now look at like more complex representation. And these advanced plots not only summarize the distribution of one variable, but can also be segmented by adding categorical variables. And this layered visualization provides a richer context, enabling you to see how different groups compare in terms of their overall data distribution. And now let's have some demo. Welcome to the multivariate analysis. It extends bivariate analysis by examining interactions among multiple variables simultaneously. And we begin by enhancing our analysis. Uh, for instance, we can use group by function of the, let's say, garage cars, and apply the following aggregations. For sale price, we'll calculate mean, median, standard deviation, and count. And for the area, we calculate mean and median. Using NumPy, we can do so. As for the 3D, we can apply something like this. So we can use our own dataset or use with the existing one. We can zoom in, zoom out, and take a look at the data. Yeah, like this. Rotate. Yeah, we can do so. Keep in mind that we also have the overall quality here as a color. Yeah, and we can do so by using Plotly. I really like Plotly for 3D plots, interactive plots. You can rotate and play around with this. You have the data available when you like point the mouse at the point. As for the violin plots, so let's take a look how to plot them. You can do so by calculating value counts. We can calculate the violin plot here by providing all the necessary values. Yeah, the neighborhood as a separator here at X, and the separator within would be the overall quality and the sale price by neighborhood and overall quality. So here you have the colors, the overall colors, and the neighborhood, and now you can see it, the sale price by neighborhood and overall quality. And that's it for this part of the demo. Okay, but what if you do not want to spend a lot of time building visualizations? You might think, well, since I know the type of the data and these approaches are standard, why not automate this? And that's a great question because there is an automation in exploratory data analysis. And if you're either lazy or you want to save some time and be happy like this cat, you can use it, of course. Uh, Automation in EDA is a game changer, especially when dealing with massive datasets. And tools like Pandas Profiling and Sweetviz and dtale can generate comprehensive reports in seconds. Manually, it would take you hours to compile manually. And why should you automate parts of your EDA? The answer is simple. Automation saves time, provides immediate results and insights, and ensures that your analysis is consistent and repeatable across different datasets. And when you have thousands or even millions of data points, automated tools help you quickly generate visual summaries and statistical reports. This efficiency allows you to switch from these tedious calculations to interpreting the results and create solutions rather than calculating code to creating code for these calculations. However, you should know what and how is calculated. Keep in mind that those tools are not super intelligent. They just automate things that you know, that you should know. And if you automate things that you cannot interpret or cannot describe, that's not the best option. So you should keep in mind that you must know what you're automating. And if we take a closer look at some popular EDA automation tools, for example, data profiling, often seen as Pandas profiling, and it provides detailed descriptive statistics, missing value matrices and histograms and a lot of nice things. Sweetviz is particularly strong when comparing datasets, such as train and test splits, and often target analysis along with visual comparisons. And dtale, on the other hand, offers an interactive interface for in-depth data exploration, complete with filtering and sorting functionalities. And each tool has its unique strengths, and choosing the right one depends on your specific analysis needs. Okay, and why shouldn't you rely entirely on automated EDA? Automated EDA tools may miss the context and nuances of your data. They can overlook critical patterns or misinterpret anomalies if not reviewed by a human analyst. And relying only on automation may lead to passive approach when you miss opportunities for deeper insights. It's important to remember that these automated tools provide a starting point. They are excellent for initial insights, but the nuances and the context that come from manual exploration are irreplaceable. Always combine automated reports with your own manual checks to ensure a thorough understanding of the data. In this demo, we'll see how these tools work. Welcome to this demo, and we will discuss the EDA automation. So we start with the same housing data set, and no, like nothing special. We just connect to the Google Cloud and load this data set, load the descriptions. Here's everything is similar, and yeah. Let's take a look at the Pandas profiling or Y data profiling. We install it, install Jupyter extensions for this. And it goes like this. So you load the data set. For the simplicity, I created a sample of this data set just to speed up the calculations. And you create a profile report just for the data set. And you save it either to file or to display. This is how it goes. So we have a sample, and you have some missing values, correlations, and so on. So basically, you have an overview, alerts based on your data with high correlation or imbalance or missing values. That is like worth reviewing this reproduction, um, how it was calculated, and so on. Overview, like dataset statistic, variable types defined here. Variables, you can select columns, review them, or just review. So high uniqueness, high correlation here, subclasses. Again, all the information regarding your data can be found here. That speeds up your investigations. Again, let me just scroll it down because there are a lot of features here. And yep, some text, data. Moving on, yeah, sale price distribution and interactions. So you can, if you like, you can have some interaction. You can build, you can plot some interactions between whatever features you like, and you'll have it. So again, really useful, super nice. Also here you have the heat map calculation, then you can have it as a table, missing values either as count or as a heat map here, and sample. Sweetviz is another lib. Again, we install it, and it operates similarly to profiling lib that we had. So you can have the report on each variable here, similarly to what we have seen. Some missing information. Again, you can utilize it as you want. That's a lot of data here. As you can see, like the feature number and the information about this feature. And if you click here, you can have the statistics of this sale type, for instance, the sale condition. Again, this simplifies, and you don't need to calculate the whole things manually. Just use it and review your data set. Super useful. Detail, it's a bit more complicated to use. Again, you set up this thing, you read the data set and you show it, like you initialize it and you show it. That's an interactive table here, and you have like the information about each variable. You can rename it, lock it, hide it, and whatever. You have actions like show, hide columns, convert, filtrate, apply some functions, merge, stack, summarize. And you have a lot of visualizations at hand, highlighting, and all the settings. So I recommend reviewing this. If you like, maybe you'll like this better. And that's it. Thanks. Welcome back. What about visualization tools and resources? There are plenty of them. And visualizations transform raw numbers into stories, making your insights accessible to both technical and not technical audience. And visualizations are central to understanding and communicating your data insights. A well-crafted chart can make complex patterns immediately clear, guide decision making, and reveal insights that raw numbers simply cannot. Whether you're using simple bar plots or interactive dashboards, the goal is to tell a story that is both compelling and accurate. And this is why mastering visualization techniques is an essential skill in data science. Remember, a well-designed visualization can often convey more than pages of statistical summaries. Advanced visualization libs like Seaborn, Plotly, and sometimes Altair, Bokeh, or ggplot provide powerful tools to create interactive and aesthetically pleasing visualizations. In addition to their technical capabilities, it is important to consider accessibility. Keep in mind this. Using colorblind friendly patterns and palettes not only makes your visualizations more inclusive, but also enhances clarity for all viewers. The resources on this slide are excellent starting points. Please use any of this lib that fits you and try it. And in this demo, we'll explore several visualization tools and resources. And this is the demo for visualization tools. So we'll review just a couple of them. We'll have the ggplot. That is interesting to use, however, it's a bit outdated, I would say. But you can create nice looking diagrams with this. However, yeah, it is not interactive, at least here. You can use Plotly. I really like Plotly. It is interactive. You can zoom in, zoom out. You can have the information about each data point here. And that's super easy to use, similar like Matplotlib. Here you just create a scatter plot. What else? you can have these nice looking box plots with all the information just by a single line and with all the interactions that you need or might need. Again, bar plot, scatter plot, interactive, 3D. You can rotate it, zoom in, zoom out. All the different types and shapes. For instance, like the pie chart. But please do not use pie charts. They're nice looking, but they're really hard to read. For example, this one is 30% and this one is 26%. However, they might seem pretty close to each other. So yeah, they're really hard to read. As for the bokeh, I really like it. That's useful, that's nice looking, that's interactive plot. You can use it and you can create some sophisticated plots here with different sizes, with zooming in, zooming out if you like, moving around, and yeah, that's also you can create the bar plot here. Yeah, it does not support 3D scatter plots. Altair, again another lib that is very interesting to use, really easy to use, I would say, because here you can see like we created a scatter plot with different sizes, with different colors for the lot area and sale price. We could also add, I don't know, for instance, the shape here, but please don't use that because even this is pretty hard to read. If you add shape here, you'll break somebody's eyes. Just joking. If you need, you can use it. And again, here you can have this, let's say, plot, this histogram by using the binning range. It's a bit more complicated to calculate and to plot histogram here than just using something from the Seaborn. However, like you can save in different options and maybe you'll like it because you can zoom in, zoom out. Here you can zoom in, zoom out. And that's it for today. Thank you. Welcome back. What about challenges? Challenges in exploratory data analysis. Let us discuss some strategies to overcome the common challenges there. So, for missing data, you might use imputation techniques or decide to remove incomplete records if they represent in a smaller portion of your dataset. And inconsistent data formats, such as dates or units, require standardization to avoid errors. Outliers need to be carefully identified and, if necessary, removed or transformed to prevent skewed results. And when working with high-dimensional data, techniques like principal component analysis can reduce complexity and prevent overfitting. And finally, addressing data imbalance by methods like resampling or using specialized algorithms ensures that your models do not become biased towards the majority class. And implementing these strategies is crucial to ensure that your insights and predictions are both accurate and robust. And we will dive deeper into each of these challenges during the data preparation lecture. Let's have some final remarks and recap. As we are moving to the end of our session, let's summarize what we've covered. Today, we explored the fundamental concepts and techniques of exploratory data analysis. We reviewed how to inspect data, perform univariate, bivariate, and multivariate analysis, and use a variety of visualization techniques to uncover patterns and relationships. And remember, EDA is an iterative process. Each insight you gain builds the foundation for better models and more effective decision making. EDA helps you avoid common pitfalls and ensures that your data is well understood before you build any models. This iterative process will be a constant companion in your journey as a data scientist. The skill you develop here will not only enhance your technical abilities, but also empower you to think critically about the data. And to summarize, exploratory data analysis is not just an optional step. It's a necessity in any data science project. Finally, here are some resources that I highly recommend for exploration. The CRISP-DM framework, the Data Visualization Catalog, and various online guides on choosing the right visualization are excellent for expanding your knowledge. These tools and resources will serve you as your companions as you continue to refine your EDA skills and apply them to real-world data problems. It brings us to the end of today's lecture on exploratory data analysis, and thank you all for your attention. Remember, the ability to thoroughly explore and understand your data is what sets apart great data scientists. Every dataset holds a secret waiting to be uncovered. And with the skills you've developed, you are well equipped to explore, analyze, and innovate. I hope this session has provided you with not only technical tools, but also the critical reasoning needed to excel in your projects. I encourage you to continue practicing, ask bold questions, and never settle for the surface level story that your data might initially tell. Your curiosity and critical thinking are your greatest assets on this journey. I wish you all the best, and I wish you advance through the course and beyond. May your analysis be deep, your insights transformative, and the future as bright as the discoveries you make. If you have any questions or would like to discuss any of the topics further, please feel free to reach out. Good luck and keep exploring.